Alright, so today we're going to be doing problems 1.12 and 1.13 in the book. So 1.12, it says the Fourier transform of a signal x of t is defined by x of f is equal to sinc f, where the sinc function is defined as an equation 1.39. Find the autocorrelation function Rx of t of the signal x of t. Alright, so first we need to figure out, let's write down our knowns first off. Let's start with our knowns and what they're asking us first. So the knowns, we have a signal. And that signal is x of t. We know that the Fourier transform of x of t is given by sinc of f. So this is equal to x of f. So that's x of f is the Fourier transform of x of t, where x of f is equal to sinc f. And they want us to find. So these are known. We're going to find what x of t. We're going to find the autocorrelation function. So find Rx of t. Well, what is the autocorrelation function? The autocorrelation function is the integral from minus infinity to infinity of x of t times x of t plus tau respect to dt. So we're going to have to compute this. So first we have to figure out, we take the inverse Fourier transform. So to find x of t, we need to find x of t, right? So we can compute this integral. We need to find what x of t is first. We know what x of f is. To find x of t, what we're going to do is take the inverse Fourier transform, so form of sinc of f. So you can use a table to find this, and I'll put the table up here on the screen. The inverse Fourier transform of sinc of f is going to be equal to a rect of t divided by 1. And so I'll draw this graph here so you guys get an idea of what this looks like. So x of t here is going to end up being so the amplitude is going to be 1, because this is the amplitude out front. This is 1 times rect. But I just didn't put the 1, but anytime you don't have one explicitly written, you can assume that it's a 1 as a multiplier here. So rect of t. And then this distance right here, this total distance, the box is 1. So then if this is centered at 0, then this must be minus 1/2 here. And this is positive 1/2 here. So this is there and there. And so this is our x of t. And so what they're asking us to do is compute Rx of t. Well, Rx of t is equal to a rect of t. So rect of t convolved with rect t. So autocorrelation is just a function convolved with itself, really. It's no different than that. And so we can go ahead and compute this in the traditional method. So that would be like doing graphically sliding the boxes through one another. That's how you compute a convolution. Or we can use the fact that when you have two functions, so let's say x of t convolved with let's say another x, let's say x1 of t and x2 of t, right? When you have two functions that are convolved together in the time domain, in the frequency domain, that's equal to x2 of f times x1 of f, for example, or x1 of x times x2. It doesn't matter how the subscripts are changed around. Multiplication is commutative, so you can change them around basically. But here, so what we're going to do is use this principle here. Instead of convolving them and doing all those tricky methods like sliding boxes and graph methods, we'll just take the Fourier, take to the f domain, right? And then, or take the Fourier transform, take it to the frequency domain rather. Then multiply them together and then take the inverse Fourier transform, and that'll give us back Rx of t. So to do this, we're going to take the Fourier transform of this. Let's take the Fourier transform of a rect of t convolved with rect of t. So we know the Fourier transform. We know the Fourier transform of this is going to be sinc, because the inverse Fourier transform of sinc is rect. So the Fourier transform of rect must be sinc. So we're going to get a sinc f times a sinc f. And that's going to give us, when you have two functions multiplied by one another, and this inside part is the same, you get sinc squared f. Okay, now you take the inverse Fourier transform of this. The question is, what's the inverse Fourier transform of this? Well, look at the table again. The table shows the inverse Fourier transform of sinc squared is a triangle function. So you take the inverse, so Rx of t is going to be equal to the inverse Fourier transform. Fourier transform of sinc squared of f. And so all we did was, instead of computing this using the traditional method of convolution, we took the Fourier transform, we took the inverse Fourier transform to get it back to the time domain. Because this is the representation of the autocorrelation of the frequency domain. Now we have to get back to the time domain, so it acts for Rx of t, not Rx of f. So, okay, take this inverse Fourier transform. We're going to get tri of t divided by 1, right, times 1. And the graph of this one, I'm going to draw it up here. So, so now we have a height of 1, so the maximum height is going to be 1. When you plug in t equals 0, you're going to get tri of t equals tri of 0 times 1 is going to be 1. And then here, this divisor is actually for half the triangle, so for this distance here is 1 centered at 0, when the triangle is centered at 0, wherever it's centered, it doesn't matter. The distance away from where it's centered is 1, and the distance away centered here is from 1. This is minus 1, it's positive 1, with the height of 1. And so that's going to be our x of t, our autocorrelation function for this signal. So very super simple. So you can go through and do the slide method and all the other methods, but if you take advantage of the fact that time domain and the frequency domain are very closely related, sometimes it's easier to do things in the frequency domain. Here it's just multiplication, but here it's convolution. So when you can change from one section to another, it makes it easier to compute it. And this has a lot of applications, in terms of like doing simple calculations when you have time domain data, like in a digital format, and you need to do some calculations in the frequency domain, you do some correlation in the time domain, take the one domain, do the computations, and go back to the other domain. So there's lots of different reasons this is important, but this is just one of the main reasons. So this is problem 1.13. This says use the sampling property of the unit impulse function to evaluate the following integrals. So we're going to do A through D. So let's start with A. I'm just going to write them all up here. This problem going to be really straight to the point. So A is minus infinity of cosine of t, or cosine of 6t times the delta t minus 3 dt. And then B is going to be the integral from minus infinity to infinity of 10 times delta of t times 1 plus t to the minus 1 dt. And C is going to be equal to minus infinity to infinity of delta of t plus 4 times t squared plus 6t plus 1 dt. And then finally we're going to use d infinity of delta of the exponential, so e to minus t squared times delta of t minus 2 dt. So how do we solve these? So basically what we're going to do is we're going to use a principle here, principle of the impulse function, and the principle says, principle says that the integral from minus infinity to infinity of a function, so our function is x of t, here we're given a name x of t, of delta of t minus t0 is equal to dt, obviously, equal to x of t0. So it's just the function value at wherever the delta is centered at, which makes sense because the delta is 0 everywhere outside of the center value. So when you multiply, it'll be 0 except where delta t has a value, which is at wherever this time shift is. And time shift is 0, and this would just be x of t is 0. Exactly. So now let's go ahead and use this property up here. So here, this is going to be cosine of 6 at 3. So this is multiplied by 3. So it's going to be cosine of 18. Pretty simple. And then you compute that. Here we have a 10 out front, so we can factor this 10 out, right? This is a multiplier, so we're going to have 10 times 1 plus this t here is going to be 0, so it's going to be 0. This is delta of t plus 0. We plug in whatever this t0 is for x of t0, so it's going to be 1 plus 0 is going to minus 1 power. 1 plus 0 is, this is going to be 10 times 1 over 1, which is just 10. Okay, next one, this is going to be, notice that this is a plus 4, right? And here we have a minus. When it's minus t0, you just use t0. So if you have a plus 4, then you have to do the opposite, the dual of the negative of it. It's going to be minus 4. So we're going to plug a minus 4 for t. So this is going to turn into minus 4. Let's do minus 4 squared plus 6 times minus 4 plus 1, which is 16. This is minus 24 plus 1. This is going to be minus 8 plus 1. This is going to be minus 7, I believe. Hopefully I did my math right correctly in that problem. And then finally here, the last problem that we have is the exponential minus t squared times delta t minus 2. This one really tricks me up, so if it's wrong, you guys are better knowledgeable about this, but I always think about this minus as being multiplied by the result of t squared. And so when you have this minus 2 here, it's, how I think about it is like e to the minus, and then in parentheses we have minus 2, we have 2, and we have 2 squared in the print. And so then it comes in e to the minus, this is 2 squared is 4, so then this turns into e to the minus 4, which is just 1 over e to the 4th. And that's how you would go about computing problem 1.13. So super simple, super easy. Hope those guys, that was helpful. And yeah.